AM reception. Demodulation. Demodulation is the reverse process of modulation. It is where the information signal is recovered from the amplitude modulated signal and sent to the amplifier and to the speaker. The term detector is a circuit that is used to extract the information from the modulated signal. This is a simplified block diagram of an AM receiver. First, we have the RF section. This is the front end of the receiver. Its job is to detect, band limit, and amplify the received RF signal from the antenna. It will then pass through a bandpass filter and then to the mixer or converter section. The mixer or converter section downconverts the received high radio frequencies to lower intermediate frequencies. Next, another bandpass filter. And then we have the IF section. Basically, what the IF section does is it amplifies and selects the frequencies. And then another bandpass filter, and then the AM detector. The AM detector demodulates the AM wave and converts it to the original information signal. And then another bandpass filter. And lastly, we have the audio section. The audio section just amplifies the recovered information before getting it to the speaker. Receiver parameters. Selectivity. Selectivity is used to measure the ability of the receiver to accept a given band of frequencies and reject all others. Shape factor. This is abbreviated SF. It is a unitless quantity and is equal to the bandwidth, that is 60 decibels below the max signal level, divided by the bandwidth, 3 decibels below the maximum signal level. The sides of a tuned circuit response curve are known as skirts. The steepness of the skirts, or the skirt selectivity of a receiver, is expressed as the shape factor. This is the ratio of the 60 decibel down bandwidth to the 3 decibel down bandwidth. The lower the shape factor, the steeper the skirts, and the better the selectivity. Q and bandwidth. Selectivity in a receiver is obtained by using tuned circuits and filters. LC tuned circuits provide initial selectivity, and filters provide additional selectivity. By controlling the Q of a resonant circuit, you can set the desired selectivity. The optimum bandwidth is one that is wide enough to pass the signal and its sidebands, but narrow enough to eliminate signals on adjacent frequencies. This is a selectivity curve of a tuned circuit. As you can see, the resonant frequency is almost unattenuated. And then at the two half-power points, we have f sub 1 and f sub 2. These are the two frequencies at which the power is cut in half. That is why negative 3 decibels is written at the leftmost side of the table or the graph. So f2 and f1 defines our bandwidth. Bandwidth is equivalent to f sub 2 minus f sub 1. Bandwidth can also be computed by dividing the resonant frequency, f sub r, by our selectivity, or Q. Bandwidth improvement. Reducing the bandwidth is effectively equivalent to reducing the noise figure of the receiver. The formula for this is BI, or bandwidth improvement, which is a unitless quantity, is equivalent to B sub RF, or the RF bandwidth in Hertz, divided by B sub IF, or the IF bandwidth, also in Hertz. Noise figure improvement. The corresponding reduction in the noise figure due to the reduction in bandwidth has this formula. NF sub improvement is equal to 10 log BI, or the bandwidth improvement. Sensitivity. Sensitivity is the minimum RF signal level that can be detected at the input to the receiver and still produce a usable demodulated information signal. This is usually stated in microvolts of the received signal. This is also called receiver threshold. Sensitivity is dependent on the following. First, noise power present at the input of the receiver. Second, the receiver's noise figure. Third, the sensitivity of the AM detector. Fourth, the bandwidth improvement factor of the receiver. To improve the sensitivity of a receiver is to reduce the noise level. This can be done by reducing the temperature of the receiver, reducing the bandwidth, and improving the receiver's noise figure. Dynamic range. Dynamic range is the difference in decibels between the minimum input level necessary to discern a signal and the input level that will overdrive the receiver, which will result in distortion. Basically, this is the input power range over which the receiver provides a useful output. The minimum receive level is a function of front-end noise, noise figure, and desired signal quality. The input signal level that will produce overload distortion is a function of the net gain of the receiver. This is the formula for the dynamic range. Dynamic range in decibel is equal to 10 log P max, which is the maximum power at the input of the receiver that will not cause any distortion at the output, divided by P min, which is the minimum power that the receiver can receive to produce a discernible output. Fidelity. Fidelity is a measure of the ability of a communication system to produce at the output of the receiver an exact replica of the original source information. There are three forms of distortion that can deteriorate fidelity. First, we have the amplitude distortion. Next, the frequency distortion. And lastly, we have the phase distortion. Amplitude distortion. Amplitude distortion occurs when the amplitude versus the frequency characteristics of a signal at the output of a receiver differ from those of the original information signal, the result of non-uniform gain in amplifiers and filters. Phase distortion. This is caused by filtering both wanted and unwanted signals. Frequencies at or near the break frequency of a filter undergo varying values of phase shift. The cutoff frequency of a filter is often set beyond the minimum value necessary to pass the highest frequency information signals. Lastly, frequency distortion. Frequency distortion occurs when frequencies are present in a received signal that were not present in the original source information, a result of harmonic and intermodulation distortion caused by nonlinear amplification. Insertion loss. Insertion loss is a parameter associated with the frequencies that fall within the passband of a filter. This is the ratio of the power transferred to a load with the filter in the circuit to that of the power transferred to a load without the filter. By formula, insertion loss in decibel is equal to 10 log of P out over P in. Noise temperature and equivalent noise temperature. Thermal noise is directly proportional to temperature. It stands to reason that noise can be expressed in degrees as well as watts or volts. T sub E is a hypothetical value that cannot be directly measured. It is a parameter that is used in low-noise, sophisticated radio receivers rather than noise figure. It is an indication that the signal-to-noise ratio as a signal propagates through a receiver. AM receivers. Coherent receivers. For coherent receivers, the frequencies generated in the receiver, which are used in demodulation, are synchronized to oscillator frequencies generated in the transmitter. Non-coherent receivers. For non-coherent receivers, either no frequencies are generated in the receiver, or the frequencies used for modulation are completely independent from the transmitter's carrier frequency. This is also called envelope detection. Tuned radio frequency, or TRF receiver. This is the simplest designed radio receiver available with relatively high sensitivity, but it is only limited to single-channel, low-frequency applications. Tuned radio frequency receiver disadvantages. The bandwidth is inconsistent and varies with center frequency when tuned over a wide range of input frequencies. It is unstable due to large number of RF amplifiers, all tuned to the same frequency. This is an example of the block diagram of a non-coherent tuned RF receiver. First, after receiving the signal by the antenna, it will be sent through an antenna coupling network, which basically couples the impedance of the antenna to our circuit. The receiver sensitivity is improved by adding a number of stages of RF amplification between the antenna and the detector. This is followed by stages or a single stage of audio amplification. The RF amplifier stages increase the gain before it is applied to the detector. The recovered signal is further amplified by audio amplifiers, which will provide sufficient gain to operate even a loudspeaker. Tuned radio frequency receiver. Many RF amplifiers use multiple tuned circuits. Whenever resonant LC circuits tuned to the same frequency are cascaded, overall selectivity is improved. The greater the number of tuned stages cascaded, the narrower the bandwidth and the steeper the skirts. The main problem with TRF receivers is tracking the tuned circuits. In a receiver, the tuned circuits must be made variable so that they can be set to the frequency of the desired signal. Another problem with TRF receivers is that selectivity varies with frequency. Superheterodyne receiver. Heterodyne means to mix two frequencies together in a nonlinear device or translate one frequency to another using nonlinear mixing. It remains today because its gain, selectivity, and sensitivity characteristics are superior to those of other receiver configurations. This is a simple block diagram of an AM superheterodyne receiver. RF section. The RF section consists of a preselector and an amplifier stage. The preselector's purpose is to provide enough initial band limiting to prevent a specific unwanted radio frequency called image frequency from entering the receiver. The preselector also reduces the noise bandwidth of the receiver and provides the initial step towards reducing the overall receiver bandwidth to the minimum bandwidth required to pass the information signals. The RF amplifier determines the sensitivity of the receiver. It is also the primary contributor of noise and predominant factor in determining the noise figure for the receiver. The advantages of including RF amplifiers in a receiver includes greater gain, thus better sensitivity, improved image frequency rejection, better signal-to-noise ratio, and better selectivity. The mixer or converter section includes a radio frequency oscillator stage and a mixer or converter stage, which is the first detector. The mixer stage is a nonlinear device and its purpose is to convert radio frequencies to intermediate frequencies. Heterodyning happens in the mixer stage, and radio frequency are down-converted to lower IF frequencies. The IF section consists of series of IF amplifiers and bandpass filters, or IF strips. Most of the receiver gain and sensitivity is achieved in the IF section. The IF center frequency and bandwidth are constant for all stations and chosen so that there is less than any of the RF signals to be received. Detector section. The detector section converts the IF signal back to the original source information. This is also called audio detector or second detector. This can be as simple as a diode or as complex as a phase lock loop. Audio amplifier section. The audio amplifier section comprises several cascaded audio amplifiers and one or more speakers. The number of amplifiers depends on the audio signal power desired. For a large speaker, a large audio amplifier is needed or multiple audio amplifiers are needed. For a small speaker, a single low-power audio amplifier will suffice.
Superheterodyne receiver operation. First, frequency conversion. Frequency conversion happens in the mixer or converter stage, and is identical to frequency conversions in the modulator stage of a transmitter, except that the frequencies are down-converted rather than up-converted. Gang tuning. Gang tuning is the adjustment for the center frequency of the preselector and the adjustment for the LO frequency. For the high side injection, we have F sub LO is equal to our RF frequencies plus our IF frequency. For the low side injection, we have F sub LO equals our RF frequency minus our IF frequency. Let's take a look at how the receiver selects only one channel out of multiple other channels. First thing we have to look at is the preselector. The preselector blocks all but only 3 RF channels. So in here we have channel 1, channel 2, and channel 3. And it has a frequency range of 535 kHz up until 565 kHz. So the bandwidth is around 30 kHz. It is tuned in to the center frequency of channel 2, which is 550 kHz. Next, the preselector has its output sent to the mixer or converter, in which it is combined with the local oscillator. It will then down-convert those frequencies to our IF frequency. Now, the IF frequency's frequency range is between 440 up until 570 kHz. Out of those frequencies, still 30 kHz bandwidth, we will select only the middle part, the channel 2. To do that, we need to pass the signal through another filter, an IF filter. The IF filter only selects the frequencies between 450 and 460 kHz. Thus, the output of the IF filter is our filtered channel 2 signal. Local oscillator tracking. Tracking is the ability of the local oscillator in a receiver to oscillate either above or below the selected RF carrier by an amount equal to the IF throughout the entire RF band. High side injection. High side injection is our radio frequency plus our intermediate frequency, and low side injection is our radio frequency minus the intermediate frequency. Tracking error. Tracking error is the difference of the actual local oscillator frequency and the desired frequency. Typically, this is not uniform over the entire RF spectrum. Plus minus 3 kHz. This is the maximum tracking error from a domestic AM BC band receiver with a 455 kHz intermediate frequency. Electronic tuning. Gang capacitors are relatively large, expensive, and inaccurate, and somewhat difficult to compensate. Mechanically variable capacitors are now being replaced by solid-state electronically tuned circuits. Electronically tuned circuits has these advantages. They're smaller, less expensive, more accurate, relatively immune to environmental changes, more easily compensated, and lastly, they are more easily adaptable to digital remote control and push-button tuning than their mechanical counterparts. Image frequency. Any frequency other than the selected RF carrier that, if allowed to enter a receiver and mix with the local oscillator, will produce a cross-product frequency that is equal to the intermediate frequency. This is equivalent to a second RF that will produce an IF that will interfere with the IF from the desired RF. Once image frequency has been mixed down to IF, it cannot be filtered out or suppressed. If the selected RF carrier and its image frequency enter a receiver at the same time, they both mix with the local oscillator frequency and produce different frequencies that are equal to the IF. Image frequency rejection ratio. This is a numerical measure of the ability of a preselector to reject the image frequency. For a single tuned preselector, it is the ratio of its gain at the desired RF to the gain at the image frequency. For more than one tuned circuit in the front end of a receiver, the total IFRR is the product of the ratios. IFRR is equal to the square root of 1 plus the selectivity squared times rho squared, wherein rho is equal to the image frequency divided by the RF frequency minus the RF frequency divided by the image frequency. Double spotting. Double spotting occurs when a receiver picks up the same station at two nearby points on the receiver tuning dial. It is caused by poor front-end selectivity or inadequate image frequency rejection. It is harmful because weak stations can be overshadowed by the reception of a nearby strong station at spurious location in the frequency spectrum. This may be used to determine the IF of an unknown receiver. Net receiver gain. The ratio of the demodulated signal level at the output of the receiver to the RF signal level at the input of the receiver. The formula for this is the gains in decibel minus the losses in decibels. The gains can be seen in the RF amplifier, IF amplifier, and audio amplifier, and the losses is present in all other parts of the circuit like the preselector, mixer, and detector. This is a block diagram of a receiver. As you can see, the gain is present in the amplifiers and losses are present on all other parts of the block diagram. So the computation of the net receiver gain is pretty straightforward. All the gain will be added minus all the losses. Squelch circuit. To quiet a receiver in the absence of a received signal. The squelch circuit keeps the audio section of the receiver turned off or muted in the absence of a received signal. That's it for AM.